Let's start. Welcome, everyone. My name is Mukund Raghotaman, and this is the session on abstract interpretation. First talk of the session will be given by Qiuhan, who is a first-year PhD student at UIUC, and she'll be talking to us about how to get an LLM to synthesize sound abstract interpreters. Qiuhan.
Thank you, everyone. Hi, I'm Qiuhan. Thanks for coming. And I'll be presenting our work, Sound Abstract Interpreters with LLMs. This is a joint work with Avaljot Singh and Professor Gagandeep Singh. We start with the motivating example in reasoning about nonlinear operators, the ReLU function here. Suppose we want to verify the property that all the outputs of the ReLU function is always non-negative. Therefore, the most straightforward way is to enumerate all execution traces. However, the issue is there will be infinitely many inputs, which makes this method impossible. Therefore, a natural choice is to apply abstract interpretation, which is actually the only automatic approach we can adopt when we are reasoning about the highly nonlinear functions, despite we use the ReLU, the piecewise linear function here. So in this case, we can apply abstract interpretation and then categorize the input x into two cases. And then we approximate the box domain through the program until we get the approximated output for us to do the verification. And there are many more highly nonlinear functions apart from ReLU, such as JLU and ELU, which are usually commonly used in many downstream tasks. For example, the neural network verification. So the key component that enables the correct propagation in the neural network verification is a sound abstract interpreter, which is the composition of many sound abstract transformers. And to construct such kind of sound abstract interpreter is not an easy task, because we can see that for each abstract transformer, we need to go through three phases: the specification, verification, and implementation. We can get a sense of the difficulty by just looking at this example. This is a manual derivation of the Har-Sigmoid function in the de Pauli domain. And that is the Har-Sigmoid function, which is a piecewise linear function. So we can see that even for a single operator, it requires multiple pages of case analysis, geometric reasoning, and soundness proof. So there are many works that are trying to automate this pipeline. From the first phase specification, there are works focusing on symbolic synthesis and optimization-based methods, and so on. And to automate the following two phases, in 2025, our group came up with the first automatic verifier, ProofSound, which is based upon the domain-specific language constraint flow. So we can automatically verify the soundness with SMT solving. And to automate the implementation phase, we come up with the compiler Newton, which can automatically translate the abstract transformer in the domain-specific language from PyTorch code. And then you can use that PyTorch code wherever you want. So they're all pretty exciting, I would say, but that is far from enough, because there are two main problems. The first one is those modules are still isolated with each other, meaning that if we want to really automate this pipeline, we need at least 3 experts working on these 3 areas. And even we have already lowered the barrier here by providing a specification, a domain-specific language constraint flow, but that still needs a lot of expertise to write those domain-specific language. And the second problem is much more effort should be put into the first synthesis phase, because the current work, they might suffer from the limited generality and imprecision problem. So among everything, the first question we ask is, can we have an end-to-end automatic pipeline? And our answer is yes. We come up with the sound abstract interpreters with LLMs. With cell, the only thing you need to do is to input the keywords in the simple natural language to tell us which operator in which domain do you want. And then cell can provide you with the sophisticated and completely sound abstract transformers, not just mathematical expressions, but a valid domain-specific language, which can be later using our compiler Newton to translate it to the PyTorch code. And then you can integrate this PyTorch code within any downstreams without any extra efforts. And Cell is a one-size-fits-all framework, meaning that we can handle multiple abstract transformers in terms of multiple domains. So let's go into details of the design. As LLMs become pretty impressive these days, we want to make use of the potential. Therefore, the first question that pops up in our mind is, can we just simply use the naive prompt engineering? Of course, the answer is no. Otherwise, this work won't come to PLDI today. So there are two reasons. The first one is we require strict soundness guarantee. We briefly recall the formal definition of soundness here. We choose this oracle, which says that for all abstract elements in the abstract domain, the result we get by first doing the concretization and then doing the transformation should be less or equal to the result we get by first doing the transformation and then doing the concretization. So intuitively, it means that we should never miss any real behaviors. And there are two things in this oracle should have our attention. The first one is soundness must hold for all abstract elements, which will form an infinite space. And the second thing is each abstract element will abstract infinite number of concrete points. So at least these two infinity words kind of imply the difficulty of our task. And apart from this, therefore, a question that will naturally come up is, can we have something to help guide the LLM in the infinite space? And here comes our first key idea, that we come up with the principal function to measure the unsoundness. And the intuition behind this cost function is similar to that of the loss function during the model training, that instead of searching blindly, with this cost function, we can measure how far an unsound transformer deviates from being sound. And apart from this soundness guarantee, another guarantee we require is validity guarantee. This is because what we want is not just mathematical expressions, but a valid domain-specific language, which should be both syntactically and semantically correct. Therefore, combining these two requirements motivating our second key idea, that is, we formalize the whole synthesis problem as a constraint optimization problem. The objective here is to minimize the cost, but at the same time, we will enforce hard validity constraints. So now we can have a high-level sketch of our pipeline. We first prompt the model to get a set of transformers, candidates, and then we will pass it to our checkers to validate it against the DSL grammar. And then, in practice, this checker is lightweight and manually designed. We hard-coded 6 mistake patterns that are commonly observed in the early model generation stage in our experiments, such as typing errors, invalid constructs, and so on. So if a transformer fails this checker, then we will invoke an LLM-based repairer that attempts to fix it automatically. And then the transformer will be passed to the automatic verifier proof sound to finally verify its validity, and more importantly, to verify its soundness. If it's sound, then that's good. It will be output directly at the final result. But if it's unsound, then we will use a cost function to measure the degree of the unsoundness. So within this batch of transformers, we will choose a best unsound transformer based on 2 rules. The first one is it should have the smallest cost within this batch. And the second rule is it should have a smaller cost than that of the cost function during the last generation. And then this transformer will be passed to the LLM again to help guide the next round's generation. So we can see that the core of this pipeline is this cost function. Therefore, this is our final problem. How to design this kind of principled cost function? So we will illustrate our idea within a concrete example here. Say we want to synthesize the abstract transformer for the ReLU function in the box domain. We know that there are many trivially sound abstract transformers, but let's look at this one, the transformer that will always output the interval 0 to 1. It is correct for some inputs, but it is incorrect for some other inputs. For example, when the input is the interval 0 to 2, we can easily find some concrete points within the concretization of this interval that fails the soundness requirement. And same as the input 0 to 3, 0 to 4, and so on. We call all of these as counterexamples, which are essentially the abstract element that violate the soundness. And if we collect all of these counterexamples, we can form a counterexample set, A star. And this is exactly our first step. Now, if we want to measure the unsoundness of a transformer, we only need to measure the unsoundness degree of this A star set. which is equivalent to measure the contribution of each element within this star to the unsoundness, and then do the aggregation. Therefore, the question is, how do we measure the contribution of each element, of each violating abstract element within this set? Do we simply let it equal to 1? We cannot, due to two reasons. The first one is the A star could be an infinite. If we let the contribution of each element equals to 1, then the problem is reduced to counting the number of the counterexamples, which is actually infeasible. The second question, which is more important, is it will fail to capture the different contributions of different counterexamples to the unsoundness. We can better understand the different contributions here by looking at these two examples. The first one is the counterexample, the interval 0 to 2, and the second one is the interval 0 to 3. So the reason that they are classified as the counterexample is because we can always find some concrete point lying in the sub-area of the concretization of these two abstract elements that violates the soundness requirement. And we'll visualize the sub-area here by the colorful shady region. So we can see that each violating abstract element will have different colorful shady region here, which reminds us that each violating abstract element will contribute different degrees of unsoundness. And at the same time, it prompts us that if we want to measure the contribution of each counterexample to the unsoundness, we only need to measure the contribution of each violating concrete points that lies in this area and then do the aggregation. For example, if we want to measure the contribution of this counterexample C1, the interval 0 to 2, it will be reduced to measure the contribution of each concrete point. For example, the concrete point here, x equals to 1.5. So how do we measure this concrete point? The reason that it is a violating concrete point is its output is not correctly abstracted by the output of the abstract transformer. Or let's illustrate it from another perspective. The output of the abstract transformer, which is an abstract element, will enforce several constraints, and the output of this concrete point will violate at least one of those constraints. So this tells us two things. The first thing is outputted abstract element from the abstract transformer corresponds to several constraints. And the second thing is if we want to measure the contribution of each violating concrete point, it's equivalent to measure how much the output of concrete points violates those constraints. So in practice, when we are working on the numerical domains, we define two types of constraints, the scalar bound constraints and the phi bound constraints. And we define the measurement through the distance computation. For example, if we want to measure the violation of the concrete point x equals to 1.5, we only need to measure how much it is above the upper bound plus how much it is below the lower bound. So now we will have our finalized cost function, and this is the formalization. So more formal details can be found in our paper, but we can see that it is a highly hierarchical cost function. We first operate over the abstract elements, they operate over the concrete states, and in the end, we will operate over constraints. So it's totally principled because we only derive it based on the formal definition of soundness, and it is quantitative, it's continuous measure, which is really helpful for the guidance. And in practice, as both the set A star and the concretization set are infinite, so we will use the weighted sampling to make it feasible. So now we will have a finalized version of our pipeline. We first combine the natural language specification with the historical generation to prompt the model, and then we enforce our validity constraint through our checker. And then we use the automatic verifier to verify the soundness. And in the end, we use a cost function to help guide the search. So this iteration will keep going on until we find a sound abstract transformer or reach a maximum number of attempts. And in that case, we will use a trivially sound abstract transformer as a fallback. We know that when we're talking about the abstract transformer, there were always two metrics. The first one is soundness, and the second one is precision. So we did not explicitly encode the precision information in our pipeline, but we do observe a decent precision of the result we synthesized in our experiment. And we believe it's because of two designs in our pipeline. The first one is our prompting design. So in our prompting, we provide a few short examples with good case distinctions and DSL constructions for common patterns, such as the tension line and the second line. And this can help discourage the model from generating some trivially sound but loose relaxations, loose abstract transformers. And the second reason is because the implicit enforcement by cost function. So when we're doing the weighted sampling, the weight function we use will penalize violations near transition points more, which will encourage a correct case distinctions. And moreover, the cost function will as we talked before, our domain-specific language patterns provide some common patterns such as the second line and the tension line. Therefore, after we get a kind of precise but unsound affine, for example, the affine bonds, our cost function can penalize it until it becomes sound. So in the end of our experiments, we do the evaluation through 3 metrics: the efficiency, generality, and scalability. For efficiency, we observe that each synthesis will finish within around 2 hours maximum. And during this process, our cost function plays an important role and improves synthesis success. And in the end, the result we get consistently achieves high precision. Here are some examples. This is the decreasing trajectory of the cost function. The x-axis is the number of the iterations, and the y-axis is the value of the cost we got within that round. So we can see that despite cost function will help different models will provide different degrees of help in terms of different models, because models have different capacity. But after all, it will always help the model to help the algorithm to converge. And this is the result we get. This is the synthesized hard sigmoid transformer in the domain-specific language, which is not existed in the previous literature. And after we apply the compiler to translate that domain-specific language into a PyTorch code, this is what we can get. And this can be integrated into any downstream tasks without any extra effort. So in our experiment, we choose the neural network verification as our downstream tasks. And here are the precision results we get. We can see that for some operators which already have the existing handcrafted transformers, we can achieve the same precision, and we can synthesize more transformers which are not existed in the literature before with decent precision. And for the second matrix, generality, we test our algorithm to synthesize multiple abstract transformers for operators from linear, piecewise linear, nonlinear functions, and so on, in terms of different abstract domains, from the simple box domain to the advanced and compositional depoly domain. And we even test our pipeline to synthesize transformers for the first order derivatives, and we found that they all work pretty well. This is an example of the synthesized JLU and ELU function. We can see that they all have very careful and good case distinctions and precise and tight bonds. So in the end, we test our scalability. So we found that the peak memory we use is only 650 megabytes, and we want to emphasize that you only need to synthesize once, and you can reuse whatever you get forever. So more details can be found in our paper, and our code is totally public to everyone. Please feel free to scan them and read it if you're interested. And we hope our work can inspire efficient abstract interpretation and make it more accessible to everyone in the community. Thank you very much.
Thanks, Qiuhan. We have time for a couple of questions.
Hi, yeah, thanks for the interesting talk. So if I understood it correctly, you really just start off with natural language as input.
Yeah.
Which makes me wonder, how do you prove the soundness? Is this an auto-formalization, or how do you make sure that you verify the correct function?
Yeah, that's a good question. So in the prompting, we only need users to provide us with the prompt in the natural language. But what model will give us is a domain-specific language. That's why we design the pipeline through checker and so on. And then after we get this domain-specific language, we can use an automatic verifier. And that verify soundness is totally based on this domain-specific language. It will translate it into several constraints and use the SMT solver to verify it, so that the verification is not based upon the natural language description.
So thanks for the talk. I assume your framework can generate the abstract transformers for any arbitrary neural network activation functions, right?
Yes, theoretically we can.
So basically for all the, for instance, like tanh dot product in the transformer architectures, you can also verify, right?
Yeah, so that's a good question. We showed that we can synthesize a lot of highly nonlinear functions in the slides, but actually we do manual verification and manual cost computation there because currently the SMT solver cannot support the constraints within the nonlinear computations.
But you can use the D-Real solver to resolve
the
that,
D-Real solver will have a relaxation strategy, the delta soundness. The delta soundness is not what we want because we require a strict soundness instead of some, oh, it might be sound, or within the delta it might be sound. That's not what we want. We tried that as well, though, but we didn't use that in the end.
Okay, but you remember that, so there is another work called DeepT, which it can also like generate sound bonds for, you know, for generating the abstract transformers for bounding the tanh function or whatever dot product in the transformer architectures. So I think they have proven their bound is sound. So I think it's along the same line of work.
I'm not sure whether I have read that, but I have read a similar work which also use that solver. But in that work, you will extra apply a relaxation strategy to ensure the soundness. But that will also cause some imprecision. So we think the best way here is just to do the manual verification, unless there is a better solver which can help us to do it.
But how do you guys do the manual verification? By using Lin and theorem?
No, we just manually derive write the bonds in a mathematical way and to verify it.
Okay, I see.
Yes.
Thank you.
Thank you.
All right, I think that's time. Thanks, Qiuhan.
Thank you.